So let's get started. Upcoming schedule is pretty intense in this class. We had our first week and a half or so of not too much going on, and it's all kind of fallen on us in a short period of time. So we have our exam on Friday. We have our assignment due tonight. We're getting a new assignment today that's going to be due next week. This one will not be a coding homework. I want to allow people to focus more on the exam. So this is a written homework and a much smaller homework compared to the one that you're currently working on. We'll go back to some bigger homeworks, and we're kind of going to alternate a little bit early on of more difficult, less difficult, more difficult, less difficult. But this is going to be hopefully seem like a little bit of a break from something that's a lot of work. We have our review period tomorrow. So today is the last day of new content before the exam. Please do come prepared with as many questions as possible for tomorrow. That way we fill the time and I can draw out as much as I can, go over some practice problems. If you want me to come up with any practice problems that are relevant to a particular area of your interest, send me that email in advance so that I have a chance to look up some of those practice problems or create them. I have a limited ability to do that in person. I can usually come up with something, but if it's more complicated than that and I want to use the exact right example for your question to best address that, the sooner I know, the better I can do it, identifying the best example to help you with that question. What else? There was something else. Yeah. So as you know, I've been recording all of my lectures and they're up on my YouTube channel. One thing I want to make you all aware of, if you haven't had a chance to peruse that yet, is this is not the first time I have taught and recorded this class. So you can do something like find, I don't do a good job of documenting this, but you can go find the exam review of the last time I taught this course and see what kinds of questions that other students asked as we covered very similar content to this ahead of the exam that you will be taking that is reasonably similar to the exam that they took. So that review that they did is going to be relevant to the review that you have. So that may be useful to you. So it's just another opportunity you have that you want to make you all aware of it. Any questions about studying for the exam, about anything from the study guide that is not a question-based, but just something that would help you to study over the next couple of days, or anything that we've been focusing on that is blurry? And any questions before we dive back in? Yeah.
You have to create another iterator?
Yes, you will need iterators for both the doubly and circular linked lists. They should not be significant changes over the singly linked list iterator, because a lot of them are just calling the methods. If the methods handle the difference of you're calling a remove, then the differences should be in the differences in the remove between the different linked lists, not embedded in the iterator. Yeah.
Did you say there is a study guide for the exam?
Yes, it's up on Canvas and modules.
Thank you.
And that will be true for every exam. And remember that you also get a sheet of notes, not a note card. If I accidentally refer to a note card somewhere, that's me in the past. I've transitioned to a full sheet of notes because that's how I design exams now, is I want that sheet of notes to not just, you look up the answer and it's on the sheet of notes. That is the prior knowledge that you need to be able to answer the questions.
Front and back?
Yeah.
Okay.
Yeah, I don't want to constrain too much. As much as you can get on there, don't care. Question?
So we need to create another area for this assignment?
Yeah, a couple of them, one for the doubly linked list, one for the circular linked list. It should be very few lines of change. Is that not embedded in the assignment? I could have sworn it was embedded. It's not there. If it's not there, don't worry about it. It's due tonight. And I don't want to put new requirements on people the day something is due. That's not fair to you. All right, if it's not there, don't worry about it. Other questions or concerns? All right. We were in the middle of some practice functions last time. we saw what a logarithmic scaling looked like. I wanted to take just a little bit more time and talk about that logarithmic scaling because it looked like this was something new to most people and you hadn't really seen something like this before. So if we were to graph a logarithm, about what does it look like? You could describe that in words, what a logarithmic graph looks like. Yeah,
Isn't it, going down towards zero exponentially?
that would be an inverse function.
Or,
So you're thinking of something that looks more like this.
or rather, I mean, the other way, where it's going towards zero.
Yeah, so we call this an inverse.
Oh,
If it's. So we want to start at 0. And we want to do something like that, not ever flattening out completely, but it's something that is going to, for every +1, this would be log base 2. For every time this y-axis increments by 1, the x-axis is going to double. And that will be consistent across the entire function. Every time we add 1 here, the total amount of space is going to double before we get to that point on the logarithmic scaling. And that again is log base 2, but log base 2 is what we see in computer science a lot. And we saw that in our table when we had something like we were looking at. We had 1, 2, 3, 4, 5 on the y-axis, which is why we're seeing 1, 2, 3, 4, 5 like this. And then we see that this is 1, 2, 4, 8, 16. We're seeing this double. So for every +1 on the y, we have a ×2 on the x. So that just maps to what we see visually right here. And then when we compare that back to the code, this is saying for every +1 that we go through in this loop, every time we loop around, every instance of the loop that we run, we're going to be handling twice as much data. Our counting variable, as we've thought of this being before, is doubling. So it's the opposite of what we're used to. It's the inverse of what we're used to and how we're used to thinking about that. But every pass through the loop is going to handle twice as much data. And we can see this if we draw out one of the kinds of structures that we will eventually be looking at in this class, which is a tree structure. So I have a question as I draw this out to hopefully make this make a little bit more sense. Have we seen any kind of tree structure like this before? And we'll go way deep into this later in the course, but for now. Does this look somewhat familiar? Or have you seen something like this maybe? Now what I want to do is I want to store numbers in order such that the middle number is right here. Everything smaller than the middle number is over here. Everything larger than the middle number is over here. But that's going to be the same case when I look at any subtree. Of the numbers that are stored here, the middle number will be here. Everything less than the middle number is going to be over here. Everything greater than the middle number is going to be over here. So that ends up giving us a structure that looks something like this. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So now the middle number is the first place you look. And this allows you to play a very interesting guessing game. I'm thinking of a number between 1 and 15. How many guesses will it take you to guess the number that I'm thinking of? For sure. If you were to follow something like this diagram. Yeah.
would it be 4?
Yeah, it's 4 guesses. Because this number is less than 16, it's going to take us 4 guesses to get there. The depth of this tree is the height of this graph. And the number of nodes in this tree is the amount of space in the X here. So if this is depth 0, 1, 2, and 3, your first guess would be 8. And I'll tell you, of course, greater than or less than for your guess. If it's less than, you'll guess 4. If I say greater, you'll guess 6. If I say less than, you know it has to be 5. There's no number that I could pick between 1 and 15 that you could not guess within 4 guesses, because that is the depth of this tree. When I tell you greater than or less than, it tells you whether to go left or right. Yeah,
Is it just coincidence that this so happens to also line up with the binary? Like you n to the 2 or whatever.
all right, 2 to the n.
Yeah, 2 to the
It's
n.
the exact inverse of that.
Okay.
So if we flipped the x and the y, we would have exponential growth. Logarithmic is just the inverse of exponential. So now we're able to handle twice as many numbers for every level we add to the tree, which allows you to really appreciate exponential scaling, but also to recognize how efficient logarithmic scaling is. As bad as exponential growth is, that is how efficient logarithmic scaling is. So I don't want to dive too much into it, but hopefully this helps to be able to visualize what we mean when we say logarithmic growth. As we add a new level to this tree, we can handle twice as many numbers. With one extra guess, going from 4 guesses to 5 guesses, we can now handle numbers between 1 and 31. Going from 5 guesses to 6 guesses, we can now handle up to 63 numbers. Pretty crazy to think about. Now let's say I'm thinking of a number between 1 and 1,000,000. Any guesses as to how many guesses that would take? Throwing it out there, we have a guess for 8. Actually, is too low. It would take about 20 guesses. How about 1,000,000,000? It is about 30. So if you wanted to take 1/8 of the world's population, and you wanted to ask and be able to say something like, we're going to divide you in half somehow, half over here and half over there, and you want to identify which half the target person is in, you'd have to do that process about 30 times to identify the exact person, if you could divide them in half. Yeah. And the reason for this is, as an approximation, 2 to the 10th is 1024, which we're used to thinking about the world in base 10, so it's about 1,000. A little bit more than 1,000. 2 to the 20th is about 1,000 times 1,000, which is 1,000,000. 2 to the 30th, 1,000 times 1,000 times 1,000, which is about 1,000,000,000. So scaling is really interesting. Anyway, that's totally an aside. But it's useful when we start talking about complexities, because as we start talking about trees, then logarithmic growth is going to start becoming very common. So it's useful to, if you do see it in your code and we say this is logarithmic growth, that's what we're talking about. All right, third practice function. What is the order of this? And how do we know? Yeah,
Does it have something to do with the fact that we have I n squared and, or not squared, divided by two, and j plus n divided by two as well? Is that of an important note?
It's certainly worth looking at. The question is, what does it change, if anything? How many times is the outer loop gonna run? Starting at n over two and going, well, it's less than or equal to n. N is 10. We start at 5 and we go, well, less than or equal to 10. So we will run it at 5, 6, 7, 8, 9, 10, and then 11 to make sure that it's over. So it's proportional to n over 2. So I'm just going to leave it as n over 2 for the moment. There's a +1 or a +2 on there, but we're not going to care about that. Kind of starting with right now, +1s don't really matter too much. This is basically n over 2, and if you really want to come up with the order, it's still order n, because that divided by 2 is a constant. How about the middle loop?
J plus n over two, we don't really care about n over two, right?
Yeah, j plus n over 2 is less than or equal to n. So again, we're basically starting at n over 2 plus 1. And going, well, that is less than or equal to n, because we're adding 1 each time. So this is actually the same as that, off by 1. But it's basically the same loop. Does everyone see why this is basically the same logic? It's going to run the same number of times. The value of j is going to be different than the value of I in each of those, but we're never using that inside of this loop. So for all intents and purposes, this is pretty equivalent. This is also going to run proportional to n over 2 times, which is also order n. Yeah,
Would it run one less time, because J,
it would run, yeah, 1 less time, because we start out at 1 here and not 0.
it doesn't really matter though, because it's.
Right, yeah, if it's +1 or -1, we're still in the order, and since these are inside of each other, we're gonna end up multiplying rather than adding. Innermost loop. How many times is this running? We should all know the answer to this now. We've seen it before. Yeah,
Log base 2.
yeah, log base 2. So I'm gonna start writing log base 2 as LG. So one way to write log base 2 is just to write log and then the base. Log base 2 of n. In computer science, we shorthand this to LG. If you ever see LG, it means log base 2. So whenever we have loops inside of each other, we know we multiply. Let's first figure out the order of each of these. We said we can get rid of the over 2. This is order n. This is order n. Now that we're starting to care about orders. So we have something in order n times something in order n times something in order log base 2 of n. We multiply all that together and we get n squared log n. Technically, this should be LGN. Again, I pulled this from a source, and this source has actually made a couple of errors, and we will see the really blatant one in a couple of examples. So n squared log n is the order, and in computer science, when we say log, we're almost always talking about log base 2. Now for a challenge problem. Again, printf is the equivalent of system.out.println. This one is a little bit harder. I'm curious if anyone can see the pattern and come up with the mathematical representation of this.
Number put in.
Right. So my recommendation, if you're getting started with this, is to draw out a table. Our two important variables here are I and S, so I and S. So how many stars are we going to see relative to? How many times is this loop going to run relative to this passed in value n? So when I is 1, S is 1, because that's how we're starting out. We come into the loop, let's say n is some arbitrarily large value. We're not going to hit it. We're just going to keep going for now to see how this goes. We bump up I to 2, and we add that to S as well. So the new value of I gets added to S. So we're going to add 2 to 1 and get 3. Looping around, we're going to assume this is still true. Bump up I. Add the new value of I to S. Looping around. Bump up I. Add the new value of I to S. What's the pattern?
Up by one, and then that's just done up by I.
If we were to break this down into some expression that we could, this would be 1, 1 plus 2, 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4. So if n is 10, we would see 4 stars. If n is 6, we would see 3 stars. What is the growth of this proportional to n? Or sorry, proportional to I? If you wanted to figure this out, since the interesting thing is happening over here, what is the order of this growth?
Is that factorial
It is not factorial.
based on?
Let's draw this out a different way. I want to sum an arbitrary sequence starting at 1 and going up to n, whatever that means. 1 plus 2 plus up to n. What is the shorthand expression for that? Does anyone know off the top of their head? Yeah,
Is it? Wait, you said the shorthand?
yeah. So I want to very quickly figure out this sum. I can tell you right now with minimal mental math, the answer is 36.
8 times 7 plus.
That sum with minimal math 69. No, it should be even. 78. Is that a guess? No, now I know.
Wait, isn't it, the sum of n times the number of. That's, you can add them together and, or no?
Let's write this again, but in reverse. Now we're going to sum each column. What's the sum of each column? Yeah, 13, 13, 13, 13. Every column sums to 13. How many 13s do we have? We have n 13s. So if we wanted to do this, we know n is 12. So we're going to say that 13, this is always going to be n plus 1. So the value of 13 is n plus 1, and we have n of them. So this gives us the sub-expression n times n plus 1. What did we do to get this expression? Multiply by 2. Yeah, we just duplicated everything. So if we wanted to cross out the work that we did, that's half of the total. This is the general formula for calculating 1 plus 2 plus up to n. This will work for any value of n. So the mental math I had to do was 12 times 13 over 2. 12 times 12 is 144, an extra 12 is 156. 160 over 2 is 80. So half that distance was 2. Subtracting 2 from 80 gave me 78. A lot easier than going through and summing each one of those values. We'll see this formula come up time and time and time again, not only in this class, but all over. And if you wanted to think about why this is, you can think about drawing this as a rectangle and then basically taking a jagged edge through that where we have 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. And now it makes a lot of sense when you have something like a rectangle. The area of this rectangle is the height times the width. When we have two variables like this, it's quadratic. When you take about half of something that is quadratic, it is also quadratic. If we wanted to shorthand this and write it out, we would have n squared plus n over 2. Constant goes away, lower order term goes away. You end up with something in order n squared. So this is a quadratic increase. The issue is we don't care about the value of n as we compare it. We care about the number of stars that we're printing. We print 1 star every time we add a new term to this. So that tells us that this is the inverse of that. Just like we had the exponential growth before, and the inverse of that was logarithmic. What is the inverse of a quadratic function? Oh. Yeah, it is the square root. So the growth rate of this function, not at all a common one in computer science. This does not appear all the time. In fact, this is one of the few ways I can think of to create something that is in order square root of n. But that is the order. And it requires a little bit of mathematical reasoning and drawing out and knowing some things or being able to logic your way to that point to be able to figure it out. But I just wanted to illustrate the kind of work that you might go through in order to get from what is this code to a table to being able to logic, all right, how is this table growing? What do we know about this kind of growth? Now we've seen some experience with this. We know that it is quadratic in nature, which allows us to say, okay, going back to this, we care about how many stars are printed. When n is something on the right, we print the number of stars on the left, which flips the order and gives us the inverse of that. Yeah.
So in some mathematics, you do the like summation symbol.
Yeah.
I was trying to do that, but I felt like I was getting a little bit confused with like how that math was working out. Would you generally say to stay away from those kinds of symbols? But
I would say know the difference. So whenever you're doing something like the sum of n, whenever you do something the sum of, usually that is going to be something that happens in a loop. You're doing something over and over and over and over again. So you take the loop parameters and that becomes your sum of.
Oh.
So there is a natural tie. I wouldn't shy away from the math at all. I would just look for what is the tie between the math that I've seen and the code that I write. Because they are directly linked. They just aren't shown in a math class because it's usually not a computer scientist teaching it to you. And they haven't seen that particular application, or that's not their default way of explaining it. I like to explain math in terms of computer science concepts when I can, because as computer scientists, that's how we apply it. Questions on any of this reasoning? How we got there? Does it make sense? A few nods, a lot of, all right, so it kind of makes sense, but there's a lot left to intuitively understand it. Is that maybe a better way of phrasing it? Yeah, we'll continue to get more and more experience drawing these kinds of things out, going through examples like this as we explore more and more example problems throughout class. Okay. This is how a mathematician might kind of write that out. But we end up with the square root of n, regardless of how we go about it. All right, the last one, also a challenge problem. In fact, it's such a good challenge problem that the source got it wrong. We're familiar with the mod operator here and what that means.
That's module.
Yeah, the modulus. It means that when you divide it in, the remainder of j divided by I is 0. So j goes in, or I goes in evenly to j. If you have 6 and 3, 6 divided by 3 is exactly 2 with no remainder. So j mod I is 0. 7 mod 3 is 1, because the remainder when you divide 7 by 3, you get 2 point something, 2 and 1 over 3. That numerator is 1, so the remainder is 1. The mod is 1. Anyone want to take a guess? The outer loop is easy. How many times is the outer loop running? N times. Inside of that, we have a loop that's running I times, because we're starting at j equals I.
Which would that just be n squared?
This will end up being n squared, but why?
Because since it's happening for I times I is dependent on n.
It's not exactly I times, because we're starting out at I. Not 1. So it still ends up being quadratic, but why is that? If we were to write an expression for this. I times I is I squared. But we're starting at I. So we would subtract I. We can discard the lower order term because it is lower order. So this will run basically the equivalent of n squared number of times, because we're doing this less than n and going less than I times I, but I times I is this I and not n. Does that change anything?
Well, it's still gonna run for as many times as it's less than that.
The last time. The first time it's only going to run once. Turns out not to change anything again. And the reason it doesn't change anything again is it's very similar to the drawing that we drew out before. This is going to end up being half as much work when you do that. Starting out the first few times, you're only going to go up to a small I, but at the end, you're going to go up to an I times I, where I approaches n. The average for this is n over 2. The average of I is 0 to n. The average case is n over 2. For each one of those times, I times I based on n over 2 is going to give you still in the order of n squared number of operations. It is fewer than n squared, but it is still in that same order. Does that make sense? I think I got one total nod that time, so that tells me not really. How much time do I have? I think I can draw this out a little bit. So we are on one hand going from 0 to n. So on this axis, we're going from 0 to n. Here, we want to draw this going from when this approaches n, I times I is going to approach n times n. Right? When this is n, this is n times n. So this is going to be n times n. So the total area of this, if you take n times n and turn this into a rectangle, that would be an order n cubed. If that makes sense? N times n times n. So now the question is, what is the area under what work we are doing? So when I is 0, how much work are we doing? Not much. When n is some value, like let's say n over 4, we'll try to break this into 4 chunks and get 4 bars for how much work this is. When this is n over 4, what is I times I? N over 4 times n over 4. So, yeah, the value getting to that point times it. What is that proportional to n times n? Yeah, it's n over 16. So this bar would be 1/16 of this. So at the 1/4 point, we have the 1/16 point. That's how much work we are doing in the first fourth of this. And yes, we are growing up to that point. So this is an over approximation, but we're kind of using intro calculus types of, we're going to break this down and then make an assumption. And if we broke this down into 8 chunks instead of 4 chunks, we get something more accurate. 16 we have more, we get more accurate, but we're just trying to get a sense of, is this proportional to this area in some sense? When we have half, this is going to be n over 4. So we're going to find the n over 4 at half, and that's going to be about that much work. That's more like 1/3, 1/4 of that amount of work. At 3/4, we take 3/4 times 3/4 and get 9/16. So we're doing something like, that's just over half that much work. And then when we have n, we end up back at n times n. So the question now is this area proportional to that area? And we can see that it's approaching as we got closer and closer to this, we would have something that is in fact proportional to n cubed. So this is proportional to n squared. I'm trying a lot of you today, aren't I? Hopefully people had their caffeine before coming in. 9 o'clock classes are rough. So now we get into the interesting part of this, where inside of this, we're only doing work if j mod I is 0. If we're going up to n times n, how many times is j mod I going to be 0? Yeah,
Wouldn't it always be zero?
it is not always 0.
Not always zero.
Because we're starting at I and going up to I times I, bumping it up by 1. So when j equals I, j mod I is going to be 0.
Yes.
But then let's say something like j is 100 and I is 10, where we're bumping up j 100, 101, only every 10 times based on I is it going to be 0. If that makes sense. So how frequently compared to this is this going to be 0?
Half the time.
It actually ends up being proportional to n when we're going up to n squared. And the reason is, so we need j mod I to be 0. This was our I going up to n, and this is our j going up to n times n. How frequently is, if we could take every tick along this axis and every tick along this axis, if we divide this by this, how frequently does that go in evenly? It is n times. So it's going to be wherever n is, that's going to be the first time. And then how many times does n go into n times n? N times. So we'll start with something like 10 versus 10 squared. How many times does multiples of 10 go into 10 squared? 10 times at 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. What's the number of times that 100 is a multiple of 10? Yeah.
So is the order just end of the fourth then?
It is. Yeah, the answer is just n to the 4th. Because we do all of this work in here, not every time we do this, but every time that j mod I is 0, which is every n times. So we do n work every n times of this. So we get n times n squared times, instead of n squared again, we get n again. And that is where this source made this mistake. You can see here that they don't even give you the work to give you this is O of n to the 5th, but I had to edit the slide to say the innermost loop is only running n times, not n times, like it's saying here, because this j mod I is 0 is only going to be true n times as we go from how many multiples of this leads into this. So that is how not easy this is. Sources on the internet also lie to you. So be careful of learning everything from the internet. Even when I go to find some good examples, I have to modify them because they're not always right. Questions on any of the logic that led us to that decision? Hopefully people have taken away a little bit from this. You can start to see how math becomes relevant to computer science, the deeper in you get. It's not just logic. There's a lot of logic, and the analysis of that logic is mathematical. The next thing we're going to be diving into is sorting, because sorting is very important and is also on the ape. So we're going to be going over the 3 different sort types That could show up on the 8th. How we're going to do this is we're going to go through each of them. I'm going to describe them and walk through an example of that sort on the board in probably painstaking detail, but that's good for understanding it. Then we will go from that understanding to working in small groups. This can be pairs, it can be, if you really want to work by yourself, that's fine. Could be groups of really up to 3 if you wanted to. You're going to try to implement this yourself, and then we're going to implement it together. Once we have that implementation, the next assignment will require that implementation as we try to build sorting capabilities into our linked lists. So we're going to start with just some motivation. We have a list of integers we want to sort. Doesn't matter what the list type is. Doesn't matter if it's an array list or a linked list. It's just the fact that we need to sort some numbers that are currently in an order. Can we make any assumptions about how sorted the contents of the list are?
Probably assume that if there is no.
Yeah, we don't know. We straight up don't know the order these numbers are in. So we at least need to verify and do that. For the last couple minutes of class, take a few minutes and think about the most efficient way that you can think of to sort that list. Don't think about the easiest way for you to do it. Think about, from a computer's perspective, what would take the fewest operations to sort? And not just a small list, but as the list grows in size. So now we have a list of 1 million numbers. How could we minimize the amount of time that it takes to put those 1 million numbers in order?
Yeah, it's going to be something that's gonna happen.
There are lots of ways to sort. As you start thinking of an idea, try to come up with the order, the mathematical order of your solution. So as the list scales in size, how do the number of operations that your algorithm is needing to do to sort that list, how does that scale with proportion to the size of the list?
So that's still not that squared.
So this is something for you to think about between today and tomorrow. We will come back tomorrow and we will introduce 3 sort types that to a human are the easiest to understand and to a computer are kind of slow. Throughout the quarter, we will come up with some faster ways to sort. I have office hours starting now. Feel free to come make use of them.